we want to evaluate the surface integral, which is the double integral over the surface S of the square root of the sum of 1 and x squared and y squared differential S, where the surface S is the helicoid with vector equation given by r of u comma v, which has an x component of u cosine v, a y component of u sine v, and a z component of v, where u is on the closed interval from 0 to 4 and v is on the closed interval from 0 to 2 pi. For a quick review, for a surface S given parametrically or by a vectored valued function r of u comma v that is defined over a region R in the xy plane, the surface integral of f of x comma y comma z over the surface S equals a double integral over the region R of the function f written as a function of u and v times the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v times differential a. Notice differential S equals the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v times differential a. To begin, let's take a look at this graphically. Here is the graph of the original integrand function f of x comma y comma z, and now let's take a look at the surface of integration given by the helicoid r of u comma v. So here is the surface of integration given by r of u comma v, which is this helicoid. To determine the region R in the xy plane, we can look down on the xy plane and see the region R is this circle. And this should make sense. To determine the region in the xy plane given by r of u comma v, we would set the z component equal to 0 and have the parametric equations x equals u cosine v and y equals u sine v. To trace out the outer boundary of the region R, we can let u equal 4, which would then give us the parametric equations x equals 4 cosine v and y equals 4 sine v, and recall v is on the closed interval from 0 to 2 pi, and therefore using this slider below, this red point on the right will trace out the outer boundary of the region R, which we can see is a circle with a radius of 4. But again, u is on the closed interval from 0 to 4, which then would give us this region R in the xy plane. And now let's begin to set up the double integral over the region R. We begin by writing the original integrand function as a function of u and v. Using r of u comma v, we have x equals u cosine v, y equals u sine v, and z equals v. Performing substitution into the original integrand function, we have f of u comma v equals the square root of the sum of 1 and the square of u cosine v and the square of u sine v. To begin to simplify, we square u cosine v, square u sine v, and then factor out u squared, which gives us the square root of the sum of 1 and the product of u squared and the sum of cosine squared v and sine squared v. Cosine squared v plus sine squared v equals 1, and therefore f of u comma v equals the square root of the sum of 1 and u squared. Now let's begin to work on determining the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v. We begin by determining the first order partial derivatives of r. To determine the partial of r with respect to u, we differentiate each component of r of u comma v with respect to u, treating v as a constant. The partial of u cosine v with respect to u is 1 times cosine v or cosine v. The partial of u sine v with respect to u is 1 times sine v or sine v, and the partial of v with respect to u is 0. To find the partial of r with respect to v, we now differentiate each component with respect to v, now treating u as a constant. The partial of u cosine v with respect to v is u times negative sine v, or negative u sine v. The partial of u sine v with respect to v is u times cosine v, and the partial of v with respect to v is 1. Now that we have the first order partials, we will now determine the cross product and then the magnitude of the cross product. Let's determine the cross product using the method of expansion by minors. Let's set this up on the next slide. Recall we can determine the cross product by evaluating this 3 by 3 determinant, where for the first row we have the unit vectors I, j, and k. For the second row, we have the partial of r with respect to u, and for the third row we have the partial of r with respect to v. And now again, using the method of expansion by minors, to form the first 2 by 2 determinant, we eliminate row 1 and column 1, then multiply by the unit vector I, and then we have minus the 2 by 2 determinant formed by eliminating row 1 and column 2 times the unit vector j, and then we have plus the 2 by 2 determinant formed by eliminating row 1 and column 3 times the unit vector k. And now we evaluate the 2 by 2 determinants. For the first 2 by 2 determinant, we have sine v times 1 minus 0 times u cosine v, and then times the unit vector I, which gives us sine v times the unit vector I, and then minus, for the second 2 by 2 determinant, we have cosine v times 1 minus 0 times negative u sine v times the unit vector j, which gives us minus cosine v times the unit vector j, and then plus, for the last 2 by 2 determinant, we have cosine v times u cosine v minus sine v times negative u sine v times the unit vector k, which gives us the sum of u cosine squared v and u sine squared v times the unit vector k. Notice here we can simplify the z component. Factoring out u, we have u times the sum of cosine squared v and sine squared v, which simplifies to u times 1, which equals u. In component form, the cross product has an x component of sine v, a y component of negative cosine v, and a z component of u. And for the last step, we now determine the magnitude, which equals the square root of the sum of the square of sine v, the square of negative cosine v, and the square of u. And again, simplifying, sine squared v plus cosine squared v equals 1. The magnitude is equal to the square root of the sum of 1 and u squared. And now we have all the information we need to write the surface integral as a double integral over the region R. We have the double integral of f of u comma v times the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v times differential a, and let that differential a be du dv. And therefore the limits of integration for u are from 0 to 4, and the limits of integration for v are from 0 to 2 pi. Simplifying the integrand function, we have the sum of 1 and u squared, and now we differentiate with respect to u. The antiderivative is u times 1/3 u cubed. Now we determine big F of 4 minus big F of 0. Simplifying, we now have the integral from 0 to 2 pi of 76/3 dv. And now we integrate with respect to v. The antiderivative is 76 divided by 3v, and now we determine big F of 2 pi minus big F of 0. Simplifying, the exact value is equal to 152 divided by 3 pi, or as a decimal approximation, we have approximately 159.1740. I hope you found this helpful.